Good afternoon, good morning, good evening, good night, wherever you are. So this is the second e-lecture that is being held under the auspices of the U.S. National Committee for Radio Science. My co-host is Professor Jamesina J. Simpson from the University of Utah. I am Akhilesh Figure from Penn State. And our speaker today is Professor Sven Bilen. So he's going to talk to you about cognitive radio. During the weekend, I happened to be traveling from DC to State College, and I used GPS, and there were 3 different routes given to me. And every so often, after I had chosen a route, I would get a message saying I could choose an alternative route or not, depending on the busyness of that particular route I had chosen. So cognitive radio is somewhat similar. Okay, you have a transmitter, you have a receiver, and the frequency range, the frequency band can change depending on whichever is the frequency band best suitable at that particular time for transmission and reception. Now, this is a technology that has advanced very rapidly in the last decade or so, and Professor Bilen is an expert on this. You may want to read his a review chapter that he wrote recently. I'll put a link on for that. Professor Bilen is a Penn State alumnus. He obtained his bachelor's degree in electrical engineering in 1991. And then he went to University of Michigan, Ann Arbor, from where he obtained a master's and a PhD in 1993 and 1998. Respectively. In 2000, he joined Penn State back, where he holds multiple titles. He is a professor of electrical engineering, of aerospace engineering, of engineering design. He has been the head of the School of Engineering Design and Entrepreneurship and something else also, which I don't remember. Okay. And he has numerous research interests, primarily in systems engineering, design, and education, plasma applications, space plasmas, and micro spacecraft propulsion. So, Professor Bilen, all yours.
Thank you very much, Akhilesh and Jamsina, for the invite to give this e-lecture. As Professor Laktakia mentioned, my name is Sven Bilen, and if you look at my title, I'm Professor of Engineering Design, Electrical Engineering, and Aerospace Engineering. I guess you can look at that 2 ways. One, nobody knows what to do with me at the university, or the way that I like to look at it is that I really like doing the interdisciplinary things, the things where I pull together systems, et cetera. And so that's exactly what cognitive radio is. To be able to really think about it, you need to be able to pull things together from lots and lots of different disciplines. So if I'll start with a little bit of my own background. I was related to essentially cognitive radio and the technology that we use to be able to implement cognitive radio. So many years ago, I developed one of the first software-defined radio university courses, and that is one that still is going on at Penn State. Usually seniors and graduate level students take that course. And for me, anything with a lab, anything where you have to build things, that has to be active, hands-on approach to learning. So the students, they need to build working SDR projects, et cetera. My own background, I've built a number of different radio systems using software-defined radio platforms, et cetera, and then extended that. Had the opportunity to work with NASA's SCAN testbed, which was deorbited several years ago, but it was on the space station, and we were able to demonstrate the first cognitive link from the ground to ISS, and I'll talk briefly about that at the end of my talk. And then I've done a lot of work on software-defined ICE radar systems, so using software-defined radio techniques to be able to investigate ice sheets in Antarctica as well as Greenland. And the approach that I take, it's a systems thinking and systems design approach. So my focus is to bring together diverse elements and address things as a system. And so that's the way I work. I don't necessarily sometimes get too deep into the weeds. I let my students do that in terms of the programming or the in-depth research, but I'm always thinking about things at a systems level and how we pull together various different elements, et cetera, to be able to accomplish new and novel things. And so that, of course, is systems thinking, a systems design that values a diversity of backgrounds and expertise to be able to do the truly innovative things. So that comes to my mantra. I believe that innovation happens at the interfaces of disciplines. So getting back to why am I in 3 departments? Why do I focus on systems? It's because I really believe that that's where things happen and innovation occurs. And I love being in that space. So we'll see how that kind of comes about as I go through some of the material that I'm presenting here. So let's think a little bit about the problem. So I think Akhilesh talked a little bit about, oh, hey, I'm here and I've got some different routings and things like that. Right now, currently, we've got an unbelievable number of standards for terrestrial communications. So, I mean, if I asked you to start thinking about how many different communication standards you today used yourself, you're probably Bluetooth. You got your earphones hooked up to your phone on Bluetooth. You might not use Zigbee, but if you're doing IoT, you might be in that space. HDTV, WiMAX, USB wireless, Wi-Fi, of course, 5G, et cetera. And I could go on and on and on about the different kinds of standards that exist out there. All of them have different modulation schemes, work in different frequency bands, have got different security protocols, et cetera. And so that tends to be a challenge, and we'll talk about how we might be able to address that. With respect to cell phone standards, right, we're currently at 5G. People are beginning to talk about 6G. These communication standards change every few years, and every time they do, they require massive change outs of hardware, et cetera, where companies want to go to and are beginning to go to is the ability to essentially put new waveforms onto existing hardware, et cetera, so they don't have to change that out. One of the things that's, again, I do things in space, and some of the systems that I've worked on are space systems, so I like the application here. So I still love the news coming from the Voyager spacecraft, right, which is now left our at the very edge, or is leaving our solar system, essentially. And we're still trying to communicate with that satellite. And that happens on the Deep Space Network, and to be able to do that, they have to keep this hardware around to be able to periodically listen into what Voyager is saying. So, but then they've got to go and they've got to talk to the most recent satellites. And so that requires essentially being able to change the kind of modulation encoding schemes. And you want to do that in software so that can be a rapid change as opposed to hardware switches. And the last one, and this is probably the one that's driving cognitive radio the most, is that spectrum space itself is a precious resource, right? We're given the electromagnetic spectrum. There's certain parts of that spectrum that are very usable for radio communications. There are other parts of the spectrum which we're beginning to try to exploit, but they've got challenges themselves. And so certain places in the radio spectrum are very, very valuable from a communication standpoint. But the current paradigm is that each frequency is owned by somebody. That's why we have spectrum auctions. There were huge chunks of spectrum given out in the past to radio and TV, to different government services, et cetera. But that's the paradigm that we have, and we've got to find ways to basically deal with things within that paradigm, but incentivize people to essentially make their spectrum space available when it's not being used. So these are just a couple of the challenges that we're dealing with, and all of these are reasons for why we're working on trying to develop cognitive radio. So if I look at spectrum, I love this chart. It's made by NTIA. You can download it. It has essentially the entire frequency spectrum from 3 kilohertz all the way up to 300 gigahertz. And it documents essentially where things are. This is a US-centric one, although similar charts exist for various different in Europe and Asia, et cetera. There's wireless broadcasting for TV and radio. That's one of the primary groups that spectrum falls into. There's government services such as defense, police, transportation. We also have the ISM bands, essentially, which are unlicensed spectrum that allows ISM, scientific instruments or industrial things to communicate in certain ranges, as well as to like for instance, 2.45, the spectrum space between 2.4 and 2.5 gigahertz was made available essentially as unlicensed spectrum because that's where the microwave oven frequency is at 2.45 gigahertz. And so what was established was, hey, if you can use that space, but you've got to deal with the fact that any kind of interference would come within that. And so, what happens when you give somebody 100 megahertz of space in the gigahertz range? All of a sudden, it just fostered a massive explosion in different communication protocols, all of them having to deal with the fact that they could interfere with each other. And then, of course, there's data and phone services. So, the phone companies, the cell phone companies, et cetera, they buy spectrum space, et cetera. So if I look at just one of these here, wireless broadcasting for TV and radio, right, it exists in kind of these portions here, et cetera. And, these are large chunks of space of the radio spectrum that essentially are occupied by a single service. And we'll talk a little bit later on to see, well, okay, yes, they're occupied, people own these frequencies, but how used are these spaces actually, and are there opportunities for exploiting just this portion of the frequency spectrum? So let's talk a little about the genesis of cognitive radio. So the concept of cognitive radio was first proposed in the late 1990s by Mottola, where he looked at essentially how do you make radios more personal, essentially, in this article. It was based on his PhD thesis. And what his idea was that if a radio could sense its environment and then adapt its performance characteristics accordingly, the radio is perceiving its surroundings generally in the radio frequency range, reasoning about what it sensed. Okay, I see these radios here are operating at these frequencies, at these power levels, and then saying, well, there's a hole there. I can act on that reasoning essentially to say, well, maybe I can exploit that hole and be able to use that for my own transmissions. And so he called this process the cognitive cycle, and that the radio that performed it was called a cognitive radio. And so this is why sometimes cognitive radio is also referred to as a Mottola radio, because he's the first one to really kind of present this concept out there. So let me just give you a definition you can read, and lots of people have got different kind of definitions. This is the one that I found and put forward in the paper that Akhilesh, or the book chapter that Akhilesh had mentioned. A cognitive radio, it's an adaptive, multidimensionally aware, autonomous radio system that learns from its experiences to reason, plan, and decide future actions to meet a user's needs. So I want to give kind of an example that maybe an example, and I'm going to do this. So I'm going to be talking about a radio, and that radio, it senses its environments, and then it makes a change to its environment. And so this may happen a lot. Det liksom när jag skriver språk, så nu snackar jag lite dansk. Och så kan du förstå mig om du kan också förstå dansk. So a lot of you are probably thinking, what the heck just happened? Okay, you were listening to me, you were understanding what I was saying in English. And I shifted over to Danish. But if you were Danish, you would have immediately, and not even skipped a beat, started processing what I was saying in that other language. In a similar sense, this is what we want radios to do. Now, I might have done that because I've gone into an area where I understood that people were speaking Danish, so I would start speaking that way. You know, I grew up with a mother who didn't learn English before she came to the United States, and so quite often she would shift right into Danish, etc. I never skipped a beat, but my friends would always be like, "What is she saying?" And I was like, "Oh, she shifted language." And so this is the kind of thing that we want to be able to get into with a radio system, such that it can begin to make these changes. It senses it environment, makes these changes. The receiving thing is immediately switches over to a different modulation scheme, et cetera. It does that all autonomously, et cetera. So hopefully that was a useful example for you from just an everyday sort of experience. I think, you know, with Akhilesh, he'll know this. I mean, particularly with the number of languages in India and the use of English, I'm always interested when I'm listening to sort of Indian students, and they'll be talking English, and then all of a sudden it'll be into Hindi or into Punjabi or something else like that, and then back to English, and they know what they're talking about. But if you don't know those other languages, then it maybe is a little bit confusing to you. So think about that as the ModCon, the modulation system. All right, so this concept of cognitive radio and the implementations, it's going to fall between two extremes, and I'm going to talk a little bit about this. This concept of a Mottola radio, it exists as a theoretical concept. This is a radio that collects basically every information about all observed wireless information, and it then makes actions on that information. But I think we can understand that that can't be truly implemented in practices. But what it does is it provides an ideal to aim for in cognitive research. If we have that ideal out there, then we can think about what does it take to try to move towards that ideal, maybe realizing that we're never going to get there. The practical implementations basically say, hey, what's possible with current technology or some given amount of resources that we have right now? So we might start with just a spectrum sensing cognitive radio that might only look at the frequency spectrum and doesn't have information from other cognitive radios or doesn't deal with essentially where it's located geographically, et cetera. But these are kind of the extremes that exist in cognitive radio. Cognitive radio relies on this perception action cycle, where essentially the perceptor looks at an environment and provides that information to an actuator. That actuator then controls the signal, puts it out into the environment, and then we can measure essentially how that signal is impacting the environment and through this constant feedback loop. This is a perception action cycle, which we use all the time in any cognitive dynamic system, but we can apply this also to the cognitive radio system. So think about the fundamental tasks that a cognitive radio needs to be able to do that's based on this cycle. So you have a receiver, it's got to gather information and make an analysis of that information to determine what is the condition of the dynamic radio environment. You know, at what times are people transmitting on what frequencies, in what geographic locations, et cetera. The transmitter is going to budget its power and think about dynamically accessing that spectrum based on the information that it gets regarding the presence of what we call PUs or primary users within the thing. Those are the people, that own the spectrum currently. Like they're the ones that have the right to be in that piece of spectrum. And then there's that feedback channel that we talk about, which is constantly providing that information. And that feedback channel can go over various different pathways between the transmitter and the receiver. A cognitive radio can more effectively adapt to the radio environment if it does cooperation with other cognitive receivers. Sometimes it's possible. That's a lot of the systems that are being proposed are trying to think about how can we be cooperative with other cognitive radios. But we can also have systems that aren't cooperative, but there are many, many challenges. I'm just saying that that's where the cognitive radios do things. So let's think a little bit, or let me discuss a little bit about the evolution of cognitive radio. So let's go back to one of the drivers, and that is in the need to access more spectrum. And to do that, typically, we do that through a deregulation process. So rather than having necessarily just an ownership model, maybe we have a temporary ownership model where we deregulate the spectrum. We allow people to sell portions of the spectrum, et cetera, right? And so you're seeing this in many, many industries, whether it be the power industry, right, which is becoming deregulated in many states in the US. You saw that with the airline industry that became deregulated, the telephone industry that became deregulated. And typically, when deregulation happens, it does present challenges, but it also provides more economic opportunity and more access. So that's one of the drivers, and that spectrum deregulation is driving software-defined radio technology, because we need software-defined radio technology to enable cognitive radio. It's that cognitive radio that is going to allow us to do spectrum deregulation. So these three elements are intricately linked, and advances in each of these, spectrum deregulation is not just a technology issue, it's also a policy and legal issue, a financial and economic issue, et cetera. And so that's important to understand. So I mentioned software-defined radio, just a very brief software-defined radio 101 here. We have a system whereby we've got essentially an RF front end. That RF front end can be flexible, and we can talk about different ways. It then samples essentially the radio spectrum, and that can be done by bandwidth sampling. Sometimes as the samplers get much more capable and higher bandwidth, essentially, particularly in certain frequency ranges, you can do direct sampling, et cetera. We do channelization, sample rate conversion, basically up conversion, down conversion, et cetera. That can be done all in software. And then eventually we want to try to get everything to the software side of things. And so then output from the communication channel essentially via this baseband processing. Going the other way, we can take stuff that we want to communicate. We can then basically run it through our software, make the digital analog conversion, amplify it, and send it back out into the air. So you can see, again, a systems view of this and the things that are necessary for it, the interactions between the various different pieces, et cetera. There's been a lot of work on software-defined radio. Software-defined radio systems are now ubiquitous. You can buy, hobbyist software-defined radios for about $20. I mean, essentially the RTL SDR is an amazing device that you can buy and use in all kinds of open source software. And then there's extremely high-end software-defined radio systems used by the military and other places that are necessary for communicating over secure waveforms, et cetera. This field is just continuing to develop. It's pretty amazing. Over 20 years ago, I was one of the first people, at least within academia, to use FPGAs essentially for software-defined radio. And at the time, the architectures of these FPGA boards were not at all based on comm systems. Now, many of the FPGAs that are out there are almost expressly developed for comm applications. And as we develop things in software-defined radio as well as in cognitive radio, we're going to be moving from the hardware radio, and I'll talk about each of these through software-controlled, software-defined, then ideal, and then ultimate software radios, with what some people have referred to as different tiers on here. I'll talk just briefly about each one. Hardware radio, that's like, say, the FM radio in your or the AM radio, FM radio in your car, which hardly anyone uses nowadays, but it's going to be an FM radio. That's what it is. You can't really make it be a CB radio, et cetera. Software controlled radios are actually what is usually in most cars nowadays. This is where your display, your touch screen in the car, that's actually controlling the radio chip. but it's still going to serve as that FM radio, et cetera. It really can't move out and become a different type of radio. The software-defined radio, which is really what's exploded out there, has lots and lots of capabilities. It's able to cover substantial frequency ranges. It does that by executing software using different modulation techniques. It can be narrowband or wideband. Can pull on legacy communication schemes or make new waveforms, et cetera. Typically, they're going to store not just one waveform, but multiple waveforms, so they can move from one type of modulation scheme to another. And they can be upgraded. We can apply new replacement modules. Say if the security of a system gets compromised, you can upload a new security system. Right now, they've got different components. You know, I showed you the schematic essentially of a software-defined radio. Well, you have an antenna system, and then you have, you know, things like wideband filtering, amplification, down conversion. All of that kind of stuff exists before the analog to digital conversion. And as we'll see, as things develop, you want to move more and more of that into the software. So basically do direct analog to digital conversion. And that's where the ideal software radio comes, where essentially what you do is you just directly sample the radio spectrum as at high enough frequency that essentially you can beat the Nyquist criteria, et cetera. And then you do all of that stuff within software. And then the ultimate software radio is very similar to the theoretical Mottola radio in the concept in the cognitive radio, in that this is essentially saying, you know what, we just got a chip, we don't even have an antenna. It just basically is able to access the air and do all of the communication. It again is a theoretical concept. It's not there. You know, we can't reach that, but it at least drives us to think about how many more things can we move into software as opposed to having hardware components. So we talked about these things. Full cognitive radio, essentially the Mottola radio exists up there with the alternate software radio. We're going to be able to get us into, as we develop things from these dumb radios or the hardware radio, we need to get more cognition, intuition, intelligence into a system, develop more to these, the software radio capability to be able to move towards this ideal of a cognitive radio. Okay, let's go back to one of the first drivers for cognitive radio that I talked about. That was this concept of spectrum. So I showed you the spectrum chart for the United States, and it looked like every piece of spectrum was owned and occupied. But let's now look at what actually exists out there. If I look at essentially the TV spectrum map, we know this, you know, that in a certain region, as I flip through the channels, there'll be, and this is over the air, not your cable channel, TV, et cetera, but, you know, there would be channels that you would be able to reach, and there'd be channels that you wouldn't be able to reach. Or if you don't have familiarity with TV, think about, you know, radio, right? As you're moving down the dial of the radio, there would be gaps where you'd hear just noise, and there'd be gaps where you would see radio stations. And so there are places of the spectrum that have heavy use. There are some that have sort of medium use, and then there are some that are hardly used. Yet, this, under the current paradigm, cannot be exploited, cannot be used because somebody owns it. And so there's two things there. One, we need to motivate the owners, and two, we need to have the legal construct, essentially the policy construct, to allow that to be used. And so one of those constructs is this concept of the white space, TV white space comm systems that are able to use that. And we'll talk about some of the technologies that are needed for that. Another thing you can think about is if I look at a radio map, let's just say these are the stations here. So there's obviously going to be regions in which that radio signal is strong, and it's going to die off essentially as you move away from that. And so you can see that, you know, there are regions here, even if these signals are strong, there are regions whereby the signal is extremely weak. I wouldn't expect to be able to pick up the signal in that area. And so that would be something where that would be a place where I could exploit things geographically, et cetera. So even though nearly all spectrum is analyzed, a lot of it is not, or allocated, a lot of it is not used fully. And so therefore, let's think about how can we use that space. Here. Okay, so the opportunity to do that is to think about, okay, there are frequencies which are not used all the time or periodically used or not used at any time or periodically used. So there's some times where there's a hole given temporally, et cetera. Per the previous graph, we looked at geography. Geography could be one of those things that, where I have some things, I might have a transmission and then a mountain. Well, I can probably transmit on that same frequency on the other side of that mountain because the mountain is shielding things, et cetera. There's coding, obviously, can be used. I can use spread spectrum and other things to essentially eliminate stomping on other signals. And then, of course, angle. We can think about, being able to direct a comm signal in a certain direction and direct it in another direction, and those two directions allow me to basically use that same frequency, but because I'm firing it in different directions. So all of those are opportunities to exploit spectrum for a secondary user, what we call SU here. And this is just a graphic that kind of shows where that usage, okay, these spectrum holes may exist in various different parts of the spectrum and at various different times. So the question is, what do we need to do to exploit that? So if we look at cognitive radio, as you might imagine, we're going to use cognitive radio to be able to exploit that. So just some brief definitions. A full cognitive radio, basically, it knows every radio parameter that's taken into account to make a spectrum decision. Okay, a spectrum sensing cognitive radio may look at only the RF portion of the spectrum and may not consider power or coding and all those kinds of things. Licensed band, those are essentially devices that are capable of using licensed spectrum in addition to unassigned spectrum. And then there are some unassigned band cognitive radio. So these are devices that are only allowed to use license exempt spectrum, et cetera. So it could exist within an ISM band, et cetera. So those are the four different kind of definitions for where cognitive radio can work. So if I look at that architecture, I've got unlicensed bands, and this is something from the concept of next generation network architecture, where I've got unlicensed bands, and I have a couple of licensed bands. I'm a secondary user. I basically want to be able to access some of this licensed band here, and I'm being provided access to that by the primary owner, et cetera. There's all kinds of schemes that have to be used for that. Sometimes we talk about the need for infrastructure. So if the cognitive radios can communicate with each other, okay, then there's more use that can be used of that spectrum. And so that's kind of showing two different notions here. One is where they're not really communicating with each other. They might form an ad hoc network, et cetera, but on the other side here, they're using infrastructure essentially that then is able to access what parts of the spectrum are used. You have this concept of a spectrum broker here, which is essentially saying, okay, these things are going to become unavailable. Who wants it? How much do you want to pay for it? Various different auction schemes that can be done, et cetera. And remember, you've got to incentivize the primary users because they paid a lot of money for that space and they don't want other people there, particularly if it's going to interfere with their communications. But if it's unused, then they can be motivated economically to essentially provide that to other users. So the elements that we need for cognitive radio, I think by now you could maybe get an idea, given the overview that I provided, that we need to understand spectrum sensing and awareness. We need to look at dynamic spectrum access. We got to deal with things like interference, security, and privacy are very important. And then we'll look at a little bit at network cooperation and the concept of heterogeneous networking. So Spectrum sensing and awareness. The concept here is we want to sense and monitor spectrum to determine which bands are unused or underutilized, and also which ones can be, and those are the ones that can be used for transmission, provided we have an allowance from the primary user to do that. To do narrowband spectrum sensing, there are things to do that, like energy detection, match filtering, cyclostationary feature detection. I mean, there's a number of concepts here. I'll talk about two of them here briefly. There are newer concepts that are being exploited, and obviously more and more are being developed all the time. Things like Nyquist-based wideband sensing or compressive wideband sensing. But the choice of technique that you're using, it's going to be dependent on the available signal to noise ratio, things like the channel characteristics, of course, computational complexity and how much that drives the power usage or needs or cost of the cognitive radio. So if I look at energy detection, this is the one I think most people would kind of just naturally have an understanding of. So here's an example of essentially some a power of along various different sampling, okay? And, this could be frequency, or it could be in time, or anything else like that. And we can set different thresholds, essentially. So if we set the threshold here to 0.6, at these two sampling times or frequencies, et cetera, that's where it's going to have met the threshold. We're going to say that that channel is occupied at that time or that frequency. Down here at 0.4, we'd identified two more. And you can see down at 0.3, well, there pretty much we would say that the entire channel is occupied, et cetera, at any time or frequency. And so that doesn't really help us very much with setting the threshold down there. Newer techniques like machine learning based approaches, essentially what they're doing is they're taking a bunch of data from an existing, say, and learning from it. So they'll learn maybe that, at such a time at night, that channel becomes occupied, or these frequencies, because you've got these hopping waveforms, well, they're going to be used and we can't predict when, so we're not going to essentially use them. That's just an example of the kinds of things that can be done with machine learning, and we used some of that. I'll talk about that later on. We mentioned that dynamic spectrum access, it requires spectrum sensing, so that's detecting unused spectrum. And you want to be able to use that spectrum without causing harmful interference with the primary users that are there or other users that are using that same spectrum. I've got to have a way to manage that spectrum. So what is the most available, or what is the best available spectrum that meets certain requirements that I have for communication? I've got to have a way to be able to move between different pieces of spectrum. Okay, so my system has got to be able to move into those different frequency bands, and maintaining also seamless communication when that happens. And so, I think we all have the familiarity with our cell phones when they move from cellular access to Wi-Fi, right? Typically there's hiccups. My Starbucks app does not like when I go from my cellular access to a Wi-Fi access. I typically have to restart it. And so that's not a seamless communication transition. And spectrum sharing, well, scheduling method, et cetera, for all of these different users, et cetera. This is all elements of dynamic spectrum access. With respect to managing interference, right, we want to basically make sure that the primary users are not hampered in making their communication because of interference. And so there's a number of different ways I can do this. I can allocate different frequency bands or time slots. That's the typical standard thing that's done nowadays. But I can also work to cancel interference using advanced signal processing techniques. And so, some of the things that you'll see today that are out there, where I might have a system like what's shown here on the right, whereby I have a transmitter that's transmitting at a massively large signal that's really inflated the noise floor. And the signal that I want to see down here is completely drowned in that noise floor. And so by using some advanced signal processing techniques, I can reduce that interference after canceling it out, which then allows me to be able to get my desired reception. Other things I can do is basically mandate, different power levels. So I can tell users, okay, you can transmit, but only up to a certain power level. frequency hopping, so spreading the transmission over different frequency bands, and then spatial filtering, saying, okay, you have an ability to communicate in this region, and you have an ability to communicate in this region, and I know you're not going to interfere because there's a mountain in between, etc. With respect to security and privacy, right, that's something that we're all concerned about. There are, not everybody is an honest broker or honest player, and so you can deal with malicious attacks, you can deal with eavesdropping, etc. The concept of spectrum sensing data falsification. So let's just say you're a cognitive radio and you're in a system whereby, people are communicating back, and they're asked to open up their channel and see whether somebody's communicating at a given frequency or time. Well, there may not be people doing that, but they're going to report back maliciously and saying, oh yeah, this channel is occupied, in order to be able to use that themselves, or to be able to bid lower because it's a corrupted channel, etc. That's a kind of example of a malicious attack. And so, other concerns are things like people that don't have an authorization that are transmitting, in license bands when they don't have ability. That, this happens a lot today. Attackers can also impersonate legitimate attackers to gain access to the network. And of course, we're very concerned about privacy breaches, so sensitive information about, if you're reporting basically location information and what you're doing, and that gets leaked, that may cause privacy and concerns, etc. We I mentioned early on that it's important for cognitive radios to cooperate with each other because they become much more powerful. So here, multiple secondary users, they share their sensing to be able to improve the accuracy and reliability. They cooperate together and coordinate their transmissions. So they may say, okay, you transmit at this time, and then I'll transmit, and then you transmit again. We might transmit the same information to be able to get more data throughput or more assurance that the data has gotten through. But of course, all of this is very challenging to develop because you have a dynamic and unpredictable wireless environment. And then there's also the need to have trade-offs between cooperation and competition, particularly from the primary user. They want to maximize what kind of revenue they could get out of that space. And then the concept of heterogeneous networking, or sometimes referred to HETNet, that's the concept where you've got basically all kinds of different wireless communication standards, figuring out how to communicate effectively together with each other effectively and efficiently. And so, as I mentioned early on, the myriad standards that exist, trying to figure out how they can all communicate, and doesn't matter what I'm able to communicate on, but I can make it through. Again, think about the example that your cell phone is switching between cellular network access and Wi-Fi. Essentially, it's optimizing, usually the Wi-Fi channel to be able to, so that it can offload the data, etc. So that I hopefully is just a very brief. Obviously, there's lots and lots of challenges and research issues. I'll mention that very, very briefly. I just want to talk now myself briefly about a couple of things that I've been involved with and had the privilege to be involved with. One of them is this concept of secure blockchains for dynamic spectrum access. And so what's interesting is I think I was among the first to propose this. And it simply came from sort of a brainstorming idea, again, that thinking of different things from different fields. So I was reading an IEEE article about how blockchains really are distributed, contracting, essentially. And that made me think about the fact that, how could that be used in other spaces? And so I thought, well, how could we use that for wireless access? And so one of the things that's interesting about spectrum is that it's an expiring good. You can't go back in time and get access to that same spectrum. So if you don't use it, it just goes away. It's similar to like why Priceline came about, or hotel rooms. A hotel room is an expiring good. If you don't rent it out, if you don't have somebody in there, that you can't go back to last Saturday night and rent out last Saturday night's room. It is that value is lost. And so that's one of the things that's very interesting about spectrum space. You need to use it now. You can't store value, you can't store up spectrum. And so we wanted to propose a media access control that essentially was secure and safe, that could assign spectrum in a time frame basically on the order of microseconds. And what we did was we came up with this concept of a spec coin, which essentially uses a virtual coin currency to lease out the spectrum, and people could earn those coins essentially similar to the way they do it in Bitcoin by helping out, forming the network, figuring out other things, and then the blockchain helps with security and safety. And what's interesting, of course, about the blockchain is that it is not centralized, and so that's very, very important. So the blockchain itself is distributed, and it was a secure database of the transactions. So that was something that is very important in cognitive radio. But we also looked at the fact that, you know, obviously, if you're going to do something very complicated like doing the hash for Bitcoin, you know, that was going to take up all kinds of compute power and et cetera, which would mean that you would not be able to put these on cognitive nodes that are mobile and all those kinds of things. So that was what we did. We made a model that was distributed, it's public, there was no central authority, it was secure, and then also permissionless. And so you can read more about that in the paper. And as anything, I was kind of, you know, surprised that I was among the first to come up with this. But since then, I've seen a lot of people, a lot of research and papers out there thinking about how you can use essentially block technology for distributed cognitive radio systems. Another concept that I had developed is this concept of what I call data mining informed cognitive radio. And the concept here, and I'll just be very brief about this, but most cognitive radios look at the radio spectrum as their information source about what's going on. That is a source, but if you can think about other sources that are happening at the same time. So for instance, in space communication, if you know that you can see visually that a solar flare occurred, you can know that you can know that pretty soon there's going to be some impact from the radio spectrum, essentially, and you can see that and make decisions about that. So you don't have to just look at the radio channel to say, okay, there's going to be challenges with communicating at these frequencies, because you know some other data. In a similar sense, in this case, we looked specifically at, in those days, they were called tweets. I guess nowadays, I don't know what X calls them, but that was essentially data. And so if you knew of something that happened in a region, let's just say there was an emergency and people started tweeting out about stuff, you could know to prioritize sort of public safety channels, et cetera, as opposed to just saying, oh, wow, all these radio channels have begun to get very full. And so I call this orthogonal data. So these are data sources that are different from the Wi-Fi channels or the wireless channels themselves, but they can help you in making the decision making. And one of the most interesting and exciting things that I worked on was cognitive satellite communications. So NASA had what they call the SCAN test bed. It was on the ISS for many years. It was deorbited several years ago, basically kicked off the side and allowed to burn up. But before that time happened, my students and I, as well as some colleagues at Worcester Polytech, were able to, and colleagues at NASA, we were able to demonstrate the first cognitive satellite link, at least in the open. And so, you know, that was a challenging system, particularly fitting in with existing NASA communication technology. If you're interested in it, this is the kind of the structure here. We used a DVB waveform essentially, and then processed on it. One of the interesting things was because it was a NASA platform, we wanted to also use open source software. And so for some of the machine learning tools that we used some open source things. And after we published our paper, I got an email from the author of some of those tools that said, hey, can you tell me, was my software used in space? And I said, yes. And he said, wow, that's great. I have a a case of beer betting with this other guy that my software was going to be used in space before his. So that was kind of a neat experience there. But what we were able to show is that essentially we could have different mission profiles, whether we were in emergency mode or power saving or cooperation. And depending on that profile, we were able to get essentially be able to meet the mission of that using the data, the linked data. And we showed a marked improvement by using this cognitive system. So that was pretty exciting for us. So I'm coming to the end here. You might be saying, okay, well, what's left for me to do in cognitive radio? Well, pretty much everything. All of these areas are still things that need to be worked out. How do we allocate resources and manage those? How do we deal with interference? What are some different modalities for spectrum sensing, security and privacy, using machine learning and artificial intelligence, right? Energy efficiency from these dynamic spectrum access, cooperative communications, quality of service, all of these things, cross-layer optimization. I could go on and on and on. There is a significant amount of research that still needs to be done, but we're already beginning to see a lot of these technologies make themselves out into the direction, into cognitive radio. And so I'm very excited about the future of this field. So with that, I've come to the end of my talk. Thank you very much.
Thank you, Professor Bilen. Thank you very much. That was very interesting. And it raises several questions inside of me, but I would let the audience ask you questions first. So the audience, you have been unmuted. You can ask questions.
Hi, Sven. This is Oktay. I'm gonna go with the first question. How are you?
Good to hear you. Hear from you. Yeah.
I actually have been recently, what has really picked my attention, and I saw you mention it also, is applications of machine learning in cognitive radios. And what are some of the possibilities there? I know basically cognitive radios match well with machine learning, but are there any topics specifically that you can think of?
Yeah, so I mean, I think that's a very broad, because each of those research areas, I think, can lend itself to some sort of machine learning technique. I think the one that's being approached most often right now is, the spectrum sensing, right? So, how do I think about, or how can I use the techniques to help me determine what frequency will be available at what time or power level, et cetera. But there's other things like, so for instance, how could I, if I suddenly see some changes in something that I'm not expecting, maybe I could make an assumption that there's a malicious attack, et cetera, that's going on, or some security breach that's going on. And so those are all things that essentially I think machine learning is very good at. It's looking for anomalous situations that don't make sense and being able to highlight those. That's just two that I can think of right now.
Do you think it would also become useful in like detecting, for example, frequency hopping patterns to use the spectrum available when like there are either gaps in those hopping patterns that can be exploited?
Yeah, I mean,
Or is it just too
it can be
unpredictable?
used that way. I mean, it depends on, the smart schemes are the ones where those frequency hopping patterns are not predictable, right? And I don't know, if machine learning can predict what those hopping paths are, then I'm going to use it to bet on the stock market, right? But at least it would be able to, I don't know whether, if it's a long-term repeating pattern, then I think machine learning can pick that up. But I don't know if that, again, if it's not deterministic, whether it would be that useful.
Yeah, of course. I'm talking about deterministic patterns.
Yeah, deterministic patterns. Yeah, absolutely. I think machine learning could be very useful for that.
Thank you.
Right. Other questions? Let me ask a question. Anyway, I think it's a simple question because that's probably going to puzzle many people.
Okay.
So when I talk to you, when I give the example of the GPS, that alternate paths are picked up depending on, if there has been an accident or if there's traffic, etc. There is only one actor. The actor is a driver of the car who's getting that information, and sometimes he or she can make take an action in response to the information, and sometimes they cannot. You can't leave the road always. Okay, all right. But in this case, for the cognitive radio, there are two actors: the transmitter and the receiver. So they must have some understanding on how to change channels. And this would mean that if you bought both the transmitter and the receiver are from company A, they would maybe use one particular modality, and if they're from company B, they may use another modality. So very much like cell phones, like CDMA, for example, or whatever, WDMA, etc., right? Okay. Would this not lead to a Tower of Babel without regulation?
I get where you're trying to go with this, but I think that, and I look a little bit back at the history of Bluetooth. So when, Bluetooth first came out, right, they had all words, et cetera, and you couldn't get one thing to communicate with another, right? It was a challenge. And depending on the different companies, they had implemented the standards in different ways, maybe, or the radio channel not great or what. I don't know exactly why it was, but it didn't work very well. But that all got ironed out. And so you could get, different vendors beginning to work onto the Bluetooth, which is a frequency hopping system, et cetera. So they've been able to communicate with each other how they're going to do. And the standard essentially allows for that. And so I think there's two things that you're asking, right? You could say, there's new modulation schemes, okay, what we call waveforms, essentially, that they might be they might be proprietary, or they might be open source, et cetera. And if the companies implement those, then they would work properly. If you're dealing with things where you don't have that interoperability, then it's like when I did that, that shift to Danish, right? Unless you knew Danish, you had no idea what was going on at that time. But if you knew Danish, even if you didn't know that I was going to do that, it seemed pretty natural. And so I think what will happen is that you're going to have these systems that, we call, one of the things we do, and I didn't talk about this, and actually Oktay, I think, worked on this in the past, is modulation classification. So the idea of, okay, there's 20 modulations that could be used out there, or 20 waveforms. I don't know which the person's going to translate on, but I know those 20, and if they transmit on one of those 20, I can switch to that, right? And so that's very useful. And a lot of the QPSK and all those kinds of things, I mean, Wi-Fi channels, they're constantly switching between 16, 64, 256, 512, et cetera. And they're just doing that on the fly because they're able to they know that that's going to be one of the modulation schemes that's used. So that's kind of the way that I would describe it. Maybe not the best answer, but that's the way I would think about that.
So there has to be some regulation, whether it comes out of the industry itself, or in some cases governments impose that.
Right. And my preference would be that industry figures it out, right? That they come up with standards that they're going to use. The policy and the legal frameworks are those things that allow essentially that innovation to happen. I use the example all the time of how much economic value was made by the government releasing 100 megahertz of spectrum space between 2.4 and 2.5 gigahertz. I mean, you could argue trillions of dollars of economic value were created simply by releasing that spectrum space, right? So that's what I would argue for, is essentially allowing the people to innovate within the spectrum that they're provided, or saying, okay, as long as you don't interfere in this TV white space that got released because everybody moved to digital TV, right? But now use this space wisely, and it will create, again, additional trillions of dollars of value by simply allowing people to innovate in that space.
Thank you. All right, other questions, please. I do have another question here. Now, you're talking about, of course, these operations taking place, within a few kilometers, even maybe 100 kilometers, 200 kilometers of each other, right? Mm-hmm. Of that. And you mentioned that you were interested in implementing something similar for communication satellites, for example. And I think that would become necessary, if not now, if not in the next 10 years, then in the next 100 years, that would become necessary anyway. Yeah. So there will be a perceptible delay there. And could the effects of that delay be mitigated somehow?
Well, that depends. It depends on, what is the data that you want to send. So let's just think about something that people have familiarity with, right? Okay, so right now, in, let's just say, breaking news, right? It goes up over a satellite link, okay? And we see that delay because it's going up to a geosynchronous satellite and back down again, and that delay, and then it's usually both ways, so it ends up being, maybe a second or two, which is something that we see all the time. And so it'll say, reporting from such and so, over to you, Jim, and then Jim will be, thank you, Bob, or whatever. Now, if they said, I'm always going to send at the end of that transmission, I'm going to say, over to you, Jim. And soon as he heard the word over, the reporter on the other side started speaking, then you probably wouldn't hear that gap. That gap would be reduced because I have predicted essentially that is going to happen, right? Mm-hmm. And so, but they don't do it that way. They wait till they hear the word Jim, and then they start speaking, which is why we hear that gap, right? So in a sense where I knew what data was to be expecting, I could make predictions saying, okay, when he starts saying the word over, okay, then I know I can start talking. And I've learned that happens, and I can reduce that action cycle. So I think for certain things, for certain data, but in terms of real-time communication where I don't know what the person is going to say, et cetera, those delays are very, very difficult to deal with. And really what happens is, as we get to more interplanetary, okay, and the delay is very pronounced, it's minutes to Mars, 10 minutes, 9 minutes, something like that, I don't remember the exact value. It depends on where Mars is, essentially, obviously. The spacecraft have to make their own decisions. And again, that is a cognitive system. It's going to make decisions about what it is. It's going to collect data, and it will maybe make a decision about, hey, which data is valuable enough for me to send back, et cetera. So that's some other related elements to this whole cognitive process.
Well, some of us are dumb anyway.
Yeah.
We can't make decisions quickly.
Right.
Right. All right. Okay. Other questions, please. Well, I don't think there are other questions. Thank you very much. We will, within a couple of days, put the lecture up on 2 websites, on YouTube as well as on the URSI website. And we will urge listeners to write you directly if need be.
Okay. Well, thank you very much for the invite. I very much appreciate that. I've enjoyed putting this together, and hopefully people have found it educational, particularly if they have not had much experience with cognitive radio.
It is certainly very exciting. You know, it brings the world of NFTs and blockchain and supply chain management and electronics, actually, I should say, electronics altogether. It's something really interesting, very interesting. Thank you.
Great.
Thank you.